Okay, here's my take on the 2004 AP Physics C exam for electromagnetism, FRQ number 3. Number 3. So we've got, what do we got here? We got a current, a long straight wire with a steady current. We've got a rectangular loop of dimensions 3L and 4L, lies in the plane of the page as shown above. A long straight wire also in the plane of the page carries a constant current I. Calculate the magnetic flux through the rectangular loop in terms of I, L, and fundamental constants. Okay, well, if I grab this with, grab the wire, use the right-hand rule, grab the wire, I notice that I got flux coming out of the page. Okay, which I'll draw with dots. And notice that this flux is a function of how far away you are, right? I mean, the density of these flux, the magnetic field strength, is getting weaker as you get farther away, which means that you can't just multiply the magnetic field times the area, because the magnetic field varies depending on where you are in that area. So, well, what do we know about magnetic flux? We do know that magnetic flux is B dotted with A. Okay, so I'm going to have to integrate. Now I need to pick a little representative A that's going to be really well behaved, and you got a rectangle, so pick a little rectangle like this. Ooh, look at that. All right, and I'm just going to call this R, this distance away, like this R. So this would be a dr, and so the magnetic, now what is the magnetic field for a long straight wire? You should have that memorized. B for a long straight wire is equal to mu naught I over 2 pi r, where r is the radial distance away from that wire. And you can derive this with Ampere's law quite easily. So, but it's a good one to have memorized. So I'm just going to say, well, I'm going to integrate now. And I'm going to say B is mu naught I over 2 pi r. Okay, that's B. And then then dotted with A, and I can lose the dot product in that everything's perpendicular. This is coming out of the page perpendicular to the surface area of that loop, so don't worry about the cosine theta. Theta is 0, therefore cosine theta is 1. But anyway, and the area of that is just going to be 4L, right? Because this has a 4L and a width of dr. So 4L times dr is this little tiny, very tiny area right there. Now, this is a definite integral. Where am I going to integrate from? Well, when r is equal to L, all the way out to 4L, right? This is 1L away. This is 3L more away, so that's 4L. So from L to 4L, those are my limits of integration. R starts here and ends here as I do this integration. Let's pull all the constant stuff out. Okay, so that would be, and cancel stuff out, and when you do that you get 2 mu naught L I over pi. I just canceled this 2 and 4 and pulled all that constant stuff out. So from L to 4L, this is just going to be dr over r. Yay! Now we know how to do that. We know how to do this. You should know this integral. This is going to pop up a lot. So V is just equal to, let's write out all the constant stuff, 2 mu naught L I over pi. And this is going to be the natural log when you evaluate this of r, but r goes from 4L minus L, but remember when it's natural log you just divide it, so it's the natural log of 4. So the amount of flux in there is just going to be 2 mu naught L I times the natural log of 4 all over pi. Very nice. Okay, big ideas. What are the big ideas here? Long straight wire, you need to know the magnetic field for that. And also, how do you calculate magnetic flux? It's integral of B dot dA. That's the big idea. And how to handle that? How do you pick your A, your infinitesimal area, so that you can actually pull off the integral? And you need to know how to do natural logs, of course. Okay, so let's do part B. It says starting at time t equals 0, the current in the long straight wire is given as a function of time. Like this, where I, naught, and k are constants. The current induced in the loop is in which direction? Okay, look. This guy right here, this is an exponential function, and because it's negative k, here's what it looks like, right? If you were to graph current as a function of time, when t equals 0, we're at I naught. And as t goes to infinity, this goes to, the whole expression goes to 0. Now what does that mean? Well, if the current is going to 0, that means the magnetic field is going to 0. If this is going to 0, which means that this magnetic flux in here is getting less and less and less. So, justify your answer. Less current with time means less flux with time. Then we're going to use Lenz's law. Dictates, that's a good word to use. Dictates, if I could spell it, dictates. Okay, if this flux in here is getting less and less, this is going to induce a current to try to keep the flux the same. Okay, so if the flux is getting less and less out of the board, it's going to use the right-hand rule, try to keep flux up. So we want to oppose the rate of change, therefore induced current using the right-hand rule. And you can abbreviate, you can abbreviate stuff like this. The graders will know what you mean. You need to go, that flux needs to come up, so you need to keep the flux up, which means that it's going to be counterclockwise. And so I think that includes, you've justified why the flux is becoming less and less, because less current means less flux. Lenz's law, you're trying to induce a current to keep the flux the way it was. So that's the way I would write it if I was in a hurry, and I am. So, and I think that should get you full credit. All right, now we get to some crazy stuff. A lot of writing stuff down. It says the loop has a resistance of R. Calculate the following in terms of these guys and fundamental constants. The current in the loop is a function of time. Okay, well, E equals IR, so I equals E over R. So now I need to get, what is this induced voltage? Now we're going to use Faraday's law, right? So E equals negative d phi dt, right? Well, how much flux do we have? Let's express flux as a function of time. What the flux? Mu naught L, natural log of 4 over pi, times the current. But the current now is I is a function of time. Okay? So we want to take the derivative of this. Well, I don't want to write the constants over and over again. So I'm just going to calculate di dt, because all this is just constant stuff. So di dt is equal to ddt of I naught times e to the negative kt. Now you need to know how to take the derivative of an exponential function. Okay, so or di dt, I should say, is equal to I naught times negative k times e to the negative kt, right? Chain rule, that comes from the chain rule and all that. So now I can express my induced So now, I can go back to I. So I is equal to E. Well, if I plug this in here and solve for I get 2 mu naught L natural log of 4 times I naught times well, look, we got a negative K here, and we got a negative here from Faraday's law. So these two negatives are going to cancel out over R times pi times e to the negative kt. So there's my expression for, I think I got all the constants in there. So it's just basically taking the derivative of the current, multiplying that by all the constant stuff to get the voltage as a function of time, divide the voltage by the resistance, and now you have the current as a function of time. Yuck. All right. Now, this one's tricky. Part D is tricky, and I'm going to tell you a trick. It says the total energy dissipated. And okay, whenever they ask for energy dissipated by a resistor, or something's going on with an inductor or a capacitor or something like that, a lot of times it's good to look at power. Power is equal to the rate of change of energy, and I'll just put potential energy. I'll just use U for energy, dt, right? You should know that. Okay, so what I'm going to do is say that a little change here equals P dt, okay? So you can get, this is the energy is equal to the power that comes out of the resistance as a function, out of the circuit as a function of time, or times time. Power times time is energy consumed or used up. Okay, well, this is going to be equal to, well, what is the power? Okay, power equals I squared R. And that's going to be equal to all this crap, 2 mu naught L, natural log of 4, I naught K over RU, or R pi, I'm sorry, squared, times e to this squared, which is negative 2kt, okay, I times R. All of that, I squared R. Okay, now, I'm just going to call, I think what I did is I took all this stuff, I simplified it, and I'm just going to call it a constant A. All this stuff is a constant. I'm just going to call it A. Why am I calling it A? Because I don't want to write it down over and over again. So delta U equals the integral from 0 to infinity of this constant A times e to the negative 2 kt dt. Now you need to know how to, so this is the power function times time. And so you need to know how to integrate that. That's going to be equal to A over negative 2k. All right, that's, and then we're going to plug in infinity, e to the infinity is 0, minus, and then when I put a 0 in there, e to the 0 is 1. And I'm having to go faster because the bell just rang and my next class is coming in, and I thought I would get this done quicker. So, but anyway, you take this expression, now you got a negative 1, the negative 1 cancels with that. Equals A over 2k equals, now, when you plug in A and simplify, I'm just going to tell you what you get. You get 2k over R times mu naught L natural log of 4 I naught over pi, all of that squared. It's awful. It's an ugly expression, and I'm not going to go through the algebra. You have to go through it yourself, but that's what you do. But the big idea here is that if you want to know the total energy dissipated, integrate power over time. and then use the fact that power and through resistance is equal to I squared R. I in this case is a function of time. So you come up with a nice function of time for power. Well, it's not nice, it's horrific, but it's this guy integrated over time will give us the energy dissipated. Okay, well, that's the best I could do. And now I got to go let my second period in because they have a test. So anyway, hope that made sense. If you have questions on any of this, leave some questions in the comments or bring it to class or email me, whatever you want to do. That is all.